Welcome to Review Lecture number 10. I'm Chris Mack, the professor for this online review course of undergraduate probability and statistics. Our lecture today is on the sampling distribution. And the sampling distribution is where probability meets statistics. Probability is a branch of science and mathematics that allows us to make predictions about the behavior of individuals within a population, given a knowledge of the population as a whole. In other words, if we know what the if we know what the distribution of the population is it Gaussian, is it binomial, is it Poisson, is it exponential, etc. And we know the parameters that govern that distribution, such as the mean and the variance for a normal distribution. Then we can make predictions, probability-based predictions of any particular member of that population, or in particular about a sample. So probability allows us to describe samples given knowledge of the population. Statistics, on the other hand, turns the arrow around. We have a sample, we don't know, but we want
to infer information about the population given what we know about the sample. These two branches of mathematics, probability and statistics, meet together in terms of the sampling distribution. So let me explain what the sampling distribution is. A statistic is any quantity that we might compute from a sample. The mean, the variance, the trimmed mean, the median, the range, the interquartile range. These are all statistics, values that are calculated from measurements made on a sample. Every one of those statistics has sampling variability. If I pick a sample and I measure and compute a statistic from that sample, that statistic is unique to the sample that I have. If I were to collect a different sample, chances are very good I would get a slightly different value for that statistic. The variation of a statistic as a function of what sample I happen to pick is called the sampling variability. Now let's imagine that we picked a sample and we calculated the statistic of interest, the mean, let's say. Now I pick a different sample, I'll get a different mean. I pick another sample, I'll get another mean. Let's repeat that over and over and over again. Sample after sample after sample. I'll get a whole distribution of that particular statistic, in this case, the mean. That distribution is called the sampling distribution. If we were, in the case of an infinitely sized population, if we were to collect an infinite number of samples, then we would get a perfect description of the sampling distribution for that statistic. Here's an example, the sample mean. It's maybe the most common example, very important example as well. A sample is made up of, let's say, a series of measurements. I'll call them x1, x2, etc., all the way up to xn for a sample size of n. Well, now that we think about sampling variability, we begin to realize that every individual measurement is a random variable. x1 is the first measurement I make in my sample. If I were to take a different sample, I would get a different value for x1. Every single measurement is its own random variable. As a result, when I calculate the sample mean, I get x bar, capital X bar, which is also a random variable. Every time I pick a new sample, I'll get a new value for the sample mean. What we're going to do next is to assume that each individual measurement, xi, x1, x2, x4, all the way up to xn, each individual xi is IID, and that means independent and identically distributed. This is an assumption, and it isn't always true. It doesn't have to be true, but it's quite common that this is a good approximation. The reason is we work very hard to make our sample random. We want measurements such that the last measurement and the first measurement behave the same. We don't have to think about them differently. If we're careful about our experimental technique, we're careful about our sampling, we can ensure, at least to a very high level of approximation, that every individual measurement, xi, is in fact IID, independent and identically distributed. So, let's look at the sampling distribution of the mean under that assumption. What is the expectation of the sample mean? Well, the sample mean is a random variable, as we've just said. It's the sum of all the individual random variables of each measurement, then divided by n, the number of measurements in my sample. Let's take the expectation of both sides of this equation. A summation is linear, the expectation is linear, so I can call this 1 over n times the sum of the expectation of each individual measurement. If I assume each individual measurement is IID, then the expectation of xi is the same for every value of I. I sum up n of them, the n and 1 over n cancel out, and I get the expectation of one individual measurement. That is the population mean, mu. So the expectation value of the sample mean is equal to the mean of the population. Whenever we have a sample statistic whose expectation value is equal to the population statistic, we say that that sample statistic is an unbiased estimator. So let's look at that terminology just a little bit more. X bar, the sample mean, is an estimator for mu, the population mean. Right? It's only an estimate. It will not be an exact value. So we call it an estimator. And we will have a variety of estimators. The sample mean is not the only estimator for mu. I could look at the sample median. And it also is an estimator for the population mean. It may be a better estimate about it,
A worse estimator and other ways of thinking about it. One way of thinking about it is it an unbiased estimator. In this case, we've proven that the sample mean is an unbiased estimator of the population mean. But that's not the only criterion we'll use to judge whether an estimator is a good one. The other way we'll judge it is by the variance of that estimator. So let's look at the variance of the sample mean. We want an estimator that not only is unbiased, but also has a small variance. Why? Because we like our estimate of the sample mean, our estimate of the population mean using the sample mean to be as close to the population mean as possible. So let's calculate the variance. Here's the definition of the sample mean. I take the variance of both sides. A variance of a scalar times a random variable gives us the scalar squared times the variance of that random variable. And here is where we'll use the assumption that each random variable xi is IID, identically distributed and independent. Because as we've seen before, the variance of the sum of independent random variables is the sum of the variances of those random variables. So now I can take this variance and move it inside the equation. But the variance of each one of these is identical and equal to sigma squared, the population variance. I sum up n of them, and I get n times sigma squared. One n cancels with the n squared, and I'm left with one n on the bottom. So the variance of the sample mean is equal to the population variance divided by n. If I want the variance to be small, variance of the sample mean to be small, what do I need? I need a small population variance and or a large sample size. As I said, sigma squared is the population variance, and this formula assumes that I have an infinitely sized population. That's going to be the case for most applications in science and engineering where we're making measurements in an experiment especially.
There are some cases where the population is finite in size, and then if the sample size n starts approaching the population size, we have to modify this formula a little bit, but I'm going to ignore that. The standard deviation of the sample mean is the standard deviation of the population divided by the square root of n. This is normally what we use to describe the precision or the accuracy of our estimate of the mean, at least from a statistical perspective. And it tells us, again, what we have to do to get more precise answers. If I want to add one more digit of precision to my estimate of the sample of the population mean using the sample mean, then I have to reduce sigma x bar by a factor of 10. How do I do that? I have to increase the sample size by a factor of 100. This is why precision is expensive. Get a factor of 10 in precision requires a factor of 100 increase in the sample size. Now, with that in mind, let me define a little bit more rigorously the law of large numbers. We've talked about the law of large numbers a couple of times, but I haven't quite defined it with mathematical rigor. Let me do that now using the definition of the sample mean. Let x1 through xn be IID random variables with a mean mu and a variance sigma squared. Then I will take the sample mean x bar, subtract off the population mean mu, and take the absolute value. That is the difference between the absolute difference between the sample mean and the population mean. The probability that that value is bigger than some number, pick any number you want, including a small number, the probability that that will be bigger than a number is equal to 0 as n goes to infinity. Sounds a little convoluted, but what that's basically saying is that x bar approaches mu as n goes to infinity. This is the law of large numbers. If I increase the number of trials, then the average of the results of all of those trials tends to become closer and closer to the expected value as more trials are performed. That's the strict definition of the weak law of large numbers. An even more important theorem is called the central limit theorem. So let me spend a little bit of time talking about what this is. Again, I will assume I've got a sample with random variables x1 through xn. I will assume that each one of those random variables are IID, independent and identically distributed. They all have the same mean, mu, and a finite variance, sigma squared. This is going to be important because there are some random variables that have an infinite variance. And for those cases, the central limit theorem does not apply. But let's assume we have finite variance. This occurs for most cases of interest, but not all. Now, let me take this sample mean and convert it to a z-score, a z random variable. The sample mean x bar, subtract off the population mean mu, and divide by the standard deviation of the sample mean, sigma over the square root of n. What my central limit theorem tells me is that z is a random variable with a distribution that approaches the standard normal as n goes to infinity. What is key about the central limit theorem is this is true regardless of the distribution for the individual xi. Now, if the xi are all normal, then z will be normal no matter what, regardless of the value of n, because a sum of a linear sum of normally distributed random variables produces a normally distributed random variable. But what if the xi are not normally distributed? What if they're exponentially distributed? What if they have some other distribution that could be skewed or not skewed? It could be bimodal even. You could have lots of different shapes for the distribution. As long as they have a finite variance, what we see is that z becomes normally distributed as n gets larger and larger. That means the sample mean is normally distributed. And this is very, very powerful information. I know that my sample mean is unbiased. I know it has a certain variance. But I also now know that as n becomes infinite, that x bar is normally distributed. Now, n doesn't really have to be infinite to make this central limit theorem work for us. In fact, if n is 20 or 30, it's usually pretty good to assume that z is going to be a standard normal, unless the distribution for xi are really highly skewed. When they're a little bit skewed or reasonably symmetric, then no matter what their shape is, z is going to be very close to a normal distribution for reasonable values of n. So, we're going to use this central limit theorem because we're going to assume a normal distribution for the sampling distribution of the mean for various kinds of work that we might do. There is one little caveat, though. And in describing this caveat, I'll define a new distribution called the student's t distribution. You might have recalled from seeing that equation for z that in order to calculate z, I had to know the population variance, or the population standard deviation, sigma. Alas, we hardly ever know that. If we knew that, we would know a lot, but we tend to never know that. Instead, what we know is the sample standard deviation. And so we approximate or estimate the population standard deviation with the sample standard deviation. And instead of calculating a z-score, we calculate a t-score. The t-score is x bar minus mu divided by s over the square root of n. So we use the sample standard deviation to approximate the standard deviation of the population. However, this adds some extra uncertainty. Because we have an uncertainty in our sample deviation, the t-statistic actually has more uncertainty, more spread in that statistic than the z-statistic does, which we know to be normal for large n. Let's assume a distribution for xi. Now, we didn't do this with the central limit theorem, did we? We said any distribution xi is possible, and it doesn't affect the fact that with a large enough sample, z will become a standard normal. Here, I'm going to assume that every individual xi is normally distributed, and IID. The result is what we call the student's t-statistic, and this t-statistic is a random variable under these assumptions with the student's t-distribution and a single parameter called the degrees of freedom, df, equal to n minus 1. All right, quick story. Student. Why is this called the student's t-distribution? It's not because its purpose was to drive students crazy when they learn about it. In fact, the person who came up with this distribution, his name is William Gossett. He happened to be working for Guinness Brewery in Dublin, trying to improve the processes of barley harvesting and growth and beer making. And he was studying the experimental results using statistics. Unfortunately, because of the expense of trying a different method of growing barley or a different method of brewing, etc., the sample sizes that he used were very small. And as a result, the approximation of S instead of sigma was often had a lot of uncertainty in it because of a small sample size. And as a result, he had to develop this distribution called the student's t-distribution to account for that. Alas, Guinness didn't want him to publish the paper. Guinness was worried about revealing trade secrets, and they had had some problems with other employees publishing papers revealing trade secrets, so they had a policy of no publishing. Gossett convinced Guinness that it was okay to publish this paper, but only under a pseudonym. And he chose the pseudonym Student because he considered himself a student of statistics. As a result, the paper was published under a pen name Student, and it's become known as the Student's T distribution, although it's invented by William Gossett. The Student's T distribution is a little bit like the normal distribution. It's actually quite close in some circumstances, but with a little bit fatter tails. Here's the Student's T distribution with 4 degrees of freedom. So n is equal to 5, a sample size of 5. So you can see a very small sample size. It has the same basic shape as the normal distribution, but its tails are fatter. And that's characteristic of the fact that we have extra uncertainty that comes from estimating the population standard deviation with a sample standard deviation. Now, as the degrees of freedom grows, the Student's T distribution looks more and more like the standard normal. In fact, it becomes exactly the standard normal as the degrees of freedom goes to infinity. But whenever you have 30 or more sample size, the difference between the Student's T distribution and the normal distribution is usually insignificant. It does depend on what you call significant, your problem, etc. But I think for most people, there's no significant difference between the Student's T distribution and the normal distribution once you get above about a sample size of 30. So the Student's T distribution really is a small sample distribution, small sample size distribution. All right, that's the sampling distribution of the mean, which we know to be normally distributed because of the central limit theorem, and could be Student's T distribution for the case of a small sample size. What about the variance? If I calculate the variance of a sample, what is the sampling distribution for that variance? So again, we'll let x1, x2, etc. be IID random variables. We'll now assume that each one of them is normally distributed with a mean and a variance. Then our sample variance, s squared, will have a chi-squared statistic that we will define. So this is the Greek letter chi, and we call this the chi-square parameter. The chi-square parameter will be the sample variance divided by the population variance multiplied by the degrees of freedom, n minus 1. And this statistic is a random variable with a chi-square distribution and the single parameter n minus 1. What does that mean? Well, the chi-square distribution is very asymmetric for small sample sizes. And if you look at this, n minus 1 times s squared over sigma squared, for, say, 3 degrees of freedom, you can see it peaks at a fairly small value, but has a really long tail. As the degrees of freedom grows, s squared becomes more close to sigma squared, and chi-squared approaches n minus 1 and starts becoming more symmetric in its distribution. We'll use that distribution a little bit later. So what have we learned so far in this lecture? Well, as always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material. What is a sampling distribution, and why do we care? What is the central limit theorem? What is the sampling distribution of the mean? What is the student's t-distribution, and why would we use it? And finally, what is the chi-square distribution? Now that we have some knowledge of sampling distributions, we are, in the next few lectures, going to use these sampling distributions to enable us to make inferences about the population given a measurement made on a sample. And that's the heart of statistics. Until next time.